SwayamPrabha. Digital India. Educated India.
Welcome to lecture 25 of the course on multivariate data mining methods and applications. The title of this lecture is Convolution Neural Network. In the last two lectures, we have discussed multi-layer perceptron and then the back propagation algorithm for training the multi-layer perceptron. Now, there is a problem with multi-layer perceptron. It is not invariant to many transformations such as scaling, rotation, mirroring, etc. So, if you need a network which is invariant to such kind of transformations, then you require some alternative. In several problems where you have to deal with the images or videos or even for time series data, you require such kind of network which is invariant to such transformations. Now, one of the option is convolution network. The convolution network has some of the layers which are called convolution layers, and this network is invariant to such kind of transformations like mirroring, scaling, etc. So, in this lecture we are going to discuss the convolution neural network in detail, how to obtain the convolution layer or its role in solving different problems, etc. So, now we come to the convolution neural network. So, as I mentioned earlier, the multi-layer perceptron has the problem that it is not invariant to transformations such as rotation, scaling, mirror rotation, translation, etc. Convolution neural networks are designed to be invariant to such kind of transformations, and these networks are also called shift invariant or space invariant artificial neural networks. So, SIANN. And actually these networks are inspired by the organization of animal visual cortex. Now, how these networks work? Notice that in images there is a strong correlation between nearby pixels, and even after this kind of transformations like rotation, rescaling, etc., these strong correlations remain. Now, suppose we consider these hand written digits. So, this is your 2 and this is 3, and obviously these hand written digits are not perfect. Not perfect in the sense that different people write these digits with a variety of flavors or different flavors or in different manners. So, for recognizing these digits, you can use the nearness property. So, the nearness property also applies even after the transformations. So, even after you use the transformation, this nearness property applies. Say pixels which are highly correlated before the transformation are also correlated after the transformation. So, here is the example which we have discussed in the last lecture also. This is the original image and this is the image after the translation, the image after the rotation, mirroring or rescaling. Then multi-layer perceptron is trained for learning a map from input to output, where input is from a fixed location. So, you have input at a fixed location and then you train the model and ultimately you get the output. Then it is not feasible to train the multi-layer perceptron for all possible transformations and combinations. Say if you collect data on different pixels for this image or for this image, then you get different data. There is a transformation, a simple translation of values, but multi-layer perceptron will treat these two set of data differently and you get different outputs, different predictions. And obviously, it is not feasible to train the MLP for all such kind of transformations, and therefore, multi-layer perceptron may not be able to identify such kind of images or the digits in the presence of these transformations. So, you require some alternative approach to handle such kind of problems. Now, convolution neural network exploit information from small patches such as borders, color patches, basic shapes, etc. So, basically you have to extract such kind of information and then it utilizes these ideas through weight sharing, subsampling or receptive fields. Say how it does the weight sharing, etc., we will discuss later on. Further, it is a feed-forward neural network that learns feature engineering by itself via filters or kernel optimization. And then image is classified into one of the classes based on the identity of its main object. For example, you may classify the image into dog, aeroplane, bird or different letters in handwriting recognition. So, you may classify the images. Then convolution neural networks actually incorporate some of the layers which are called pooling layers, and it uses either maximum pooling or average pooling. We will discuss how to do this maximum pooling or average pooling in practice. Then this kind of pooling actually helps to make the net features more robust to small variations in input and reduces the computational burden. So, now once you use such kind of pooling layers, then the learned features are more robust to small variations or small transformations in the input. Remember that in multi-layer perceptron or in neural network, different hidden layers are corresponding to different features. Different hidden layers give you different features of the input data. So, the same thing applies here also. These pooling layers extract different information from the input data or different features of the input data. The advantage of these pooling layers is that these learned features are more robust to small variations. Now, the significance of convolution layers is the convolution layers exploit the spatial structure of the input data, and then each neuron is connected only to a local region of the input volume. In a convolution network, each neuron of the output layer is connected to a local region of the input, and then this captures local patterns such as edges, textures or colors. So, this is the basic objective of these convolution layers, to capture such kind of patterns, say the texture or edges or colors, etc. Then in convolution network or in convolution layer, actually the same set of weights which are called the kernel or filter is shared across all spatial positions. So, we consider the same set of weights or the same kernel or filter across all spatial positions, and then obviously it significantly reduces the number of parameters, because you are using the same set of weights to all spatial positions. And then the reduction of number of parameters in the network makes it computationally more efficient, and it reduces the risk of overfitting. Then weights sharing across the input space makes the convolution layers more robust to translations and capable of detecting features irrespective of their location. So, suppose you have a particular convolution layer to extract the edges, say, then irrespective of the location, it is capable of detecting the edges. It does not matter where the location of the edges is. Then lower layers detect the basic features such as edges or textures, and then higher layers learn more abstract features such as object parts or entire object. So, we use the lower layers for detecting the basic features, what kind of texture it has, or the shapes of edges, etc. And then we move to more abstract features, so that you can properly identify the object, the entire object. Then each neuron is connected to only a subset of neurons in the previous layer. So, it is not like a multi-layer perceptron where Each neuron is connected with all the neurons of the previous layer. Here, a particular neuron is connected to only a subset of neurons in the previous layer, and this sparsity helps in reducing the computational cost of the network. So, naturally, if you have lower number of parameters, then obviously it reduces the computational cost, and it also allows to scale efficiently large input volumes such as high resolution images or videos. So, the convolution layers enable CNNs to learn hierarchical representation of input data, achieve translation invariance. It is invariant to different transformations, and efficiently extract features relevant to the task at hand. So, you have a proper hierarchical feature extraction property. It extracts the features of the input data in a hierarchical fashion. It also achieves the translation invariance, and then it also extracts the features which are relevant to your task. Now, first we consider higher order matrices and tensor. Say X belongs to Rm. This is a column vector with m elements. So, we have discussed column vectors and matrices in one of the previous lectures. Then X belonging to R m cross n is a matrix of m rows and n columns. Now, suppose we generalize the matrix to higher dimension. So, suppose X belongs to R m cross n cross q. Now, this is an order 3 tensor, and this tensor actually contains m and q elements. So, what we do? Let us take this example of 5 cross 2 cross 3 tensor. So, this is your 5 cross 2 matrix. And then you have 3 layers arranged like this. This is 5 cross 2 matrix, then you have 5 cross 2 matrix here, then you have 5 cross 2 matrix here. So, ultimately you get 5 cross 2 cross 3 tensor. So, in all you have 30 elements, 5 into 2 into 3. Here I, j, lth element is indexed by a triplet I, j, l, where I varies from 1 to m, j varies from 1 to n, and l varies from 1 to q. And actually this tensor contains q channels of matrices, each with size m cross n. Say for instance, this tensor has 3 channels of 5 cross 2 matrices. Say color image with p cross q pixel and 3 channels, each corresponding to red, green and blue, R, G and B respectively, is an order 3 tensor. And suppose you represent a color image by a matrix, then obviously it is in grayscale, and it may not be able to give you the color information. So, the color information is lost. Then input intermediate representation and parameters in a CNN are usually tensors. Then here are different applications of CNN. You can use CNN for image classification, for image and video recognition, object detection in images. For image segmentation also you can use CNN. For medical image analysis, for natural language processing also CNN is used, or even for analyzing the financial time series one can use the convolution neural network. Now, we consider the architecture of convolution neural network. So, the nth input layer, say XL, belongs to R PL cross QL cross DL. So, usually it is an order 3 tensor, and then this input sequentially goes through a series of processing, and each processing step is called a particular layer. Now, these different layers could be convolution layer or pooling layer or normalization layer, or it may be a fully connected layer, just like the multi-layer perceptron, or it may be a loss layer, etc. Now, suppose W1, W2, so on WL minus 1, these are the learned parameters of CNN corresponding to different layers. Then we can use this model for prediction purpose. Once you train the model and you obtain these parameters corresponding to different layers, then you can use the model for prediction purpose. So, we have the first layer, then we have weights, then we move to second layer, then we have weights, and so on, L minus 1th layer, then we use these weights to get the Lth layer, and ultimately you get the output. So, starting from the input x1, the processing of the first layer with parameters w1 get x2. Then x2 is passed into the second layer with parameters w2, and so on. And finally, you obtain XL belonging to RC, say, and this gives you the posterior probabilities of x1 belonging to C categories. So, ultimately your objective is to classify x1, and then these are the posterior probabilities of x1 belonging to different categories. Then the final output of CNN prediction is argument maximum over I XIL, means you classify x1 into the class which has maximum posterior probability. So, this is the final output. So, XIL is the ith component of XL, and we obtain that I for which this XIL is maximum. Then the last layer is usually a loss layer. The loss layer corresponding to input x1. Now, suppose XL is the CNN prediction and T is the corresponding target. Then the loss function is actually the measure of discrepancy between the prediction and the target. So, this is the target value and this is the predicted value which you have obtained using CNN. And obviously, you may have some discrepancy between the prediction and target, and then you obtain a measure of discrepancy between the prediction and target, and this gives you the loss function. Then we run the network in the forward pass to get the prediction XL using current CNN parameters. And then we compare the prediction with the target T corresponding to X1. And then we continue running the forward pass till the last loss layer. And finally, we achieve a loss, say Z. Now, for training the CNN model, you have to obtain the parameters of the model. So, for that purpose, we use stochastic gradient descent algorithm. Then parameters of CNN model are optimized and updated by minimizing the loss Z. And in the stochastic gradient descent, we update Wi as Wi is updated by Wi minus eta del Z over del Wi, where del Z over del Wi is the gradient. And then we continue running the forward pass to get the predictor XL. And ultimately, we also achieve the last loss layer Z. Then in error back propagation, we compute the partial derivatives del Z over del Wi, and we also compute del Z over del Xi, just like in the multi-layer perceptron. And then del Z over del Wi can be used to update the current ith layer's parameters, and del Z over del Xi can be used to update parameters backwards. And we use this del Z over del Xi to propagate the errors backward to the I minus 1th layer. Of course, here I am not going into much details, but these are the steps for error back propagation algorithm. Then we consider rectified linear unit layer, RELU. Then this layer actually RELU performs truncation individually for every element in the input. So, we define Yijk equal to maximum of 0 Xijkl. So, you are using the truncation for all I lying between 0 to PL, which is equal to PL plus 1, and j lying between 0 to QL, which is equal to QL plus 1. Similarly, k lying between 0 to DL, where DL is equal to DL plus 1. And then we obtain dYij over dXij dl, means we are taking the derivative of Yij d with respect to Xij dl. And obviously, when we take the derivative is equal to 0 if the maximum is 0, and it is equal to 1 if the maximum is not equal to 0, the maximum is equal to xij k l. So, it is an indicator function. Indicator function I x I j k l greater than 0. Therefore, the I j kth element of the partial derivative of z with respect to x l is equal to the I j kth element of partial derivative of z with respect to y if x I j k l is greater than 0 and 0 otherwise. So, now we observe that ReLU increases the non-linearity of the CNN. So, for increasing the non-linearity of CNN, if we are using the ReLU, then basically what you are doing, you are simply truncating x I j k l, and then x I j k l, these are the features extracted by CNN layers L to L minus 1, which can be positive, 0 or negative according to input image has certain patterns or not. For obtaining convolution layer, actually we use multiple convolution kernels, and then how to get the convolution layer using multiple convolution kernels, we will come to this point. Then stride, if we consider with the input at every possible spatial location, which corresponds to stride s equal to 1. So, if we are applying the convolution operator for every possible spatial location, then we say that the stride is 1. On the other hand, if every moment of the kernel skips s minus 1 pixel locations both horizontally and vertically, then stride is s. Now, to understand this convolution layer or how to apply the convolution operator, first we just consider the method of moving averages. How we proceed in the method of moving averages. So, suppose you have this simple series. And you are taking a moving average of period 3. So, what we do, or instead of taking average, we just take a moving sum. So, what we do? We take 2 plus 4 plus 5 and write the sum in the middle against 4. So, what we get? 6 plus 5, 11. Then we move here. We take sum of 4, 5, 6. We get 15. Then we move here. 5 plus 6 plus 7. We get 18. And then 6 plus 7 plus 9. So, we get 22. Yeah. Suppose you have to take the moving average, then you divide here by 3. Now, suppose you take the average or sum of 2, 4 and 5, you get 11, and then you leave just this one digit and you start from here and take the sum. So, actually in the first case you had stride s equal to 1, here you have stride s equal to 2, because you are skipping one element. Similarly, instead of taking the sum, you can take maximum of first 3 elements, say 5, you can take 5 here, or you can take maximum of these 3 numbers, which is 6. You can take maximum of these 3 numbers, which is 7, and so on. Now, we come to the convolution operation. So, suppose we consider this 4 cross 5 convolution input. So, you have this input and you are using this 2 by 2 kernel. So, how to perform the convolution? So, first we consider the convolution with stride 1. So, what we do? We consider this matrix first. We multiply 1 by 1, 4 by 1, 2 by 2 and 5 by 2. This one is multiplied to this one, 4 to this one, 2 to this 2 and 5 to this 2, and then we add. So, ultimately you get 19. Then we move here. Again we multiply this 4 by 1, we multiply 3 by 1, we multiply 5 by 2 and 2 by 2, and you get 21. Then we move here, we apply the same operation, we get 23, and then we move here and we get 22. Then we move here. Again we multiply this 2 by 1, 5 by 1, 3 by 2 and 6 by 2, and then we add, we get 25. And finally, we get this 2 by 4 convolution output. And notice that in performing this convolution, you are using the same weights. Now, if you are using a convolution with stride 2, now this is actually the convolution with stride 1. Then for convolution with stride 2, we perform convolution here, we get 19. Then we leave this, we start from here, we perform convolution here, we get 23. And then we leave the next one, we leave one row also. So, we come to this point, we perform the convolution 3 into 1 plus 6 into 1 plus 2 into 2 plus 1 into 2, we get 15, and then we leave this, we come to here, and then we get 15. So, you get 2 by 4 convolution output with stride 2. Now, we consider maximum pooling operation. Maximum pooling operation actually reduces the dimensionality of the feature map. And here actually we take the maximum value within each pooling window. And when we apply this maximum pooling operation, what it does? It downsamples the feature map while preserving the most significant features. Now, we consider this example of 4 by 5 convolution input, and then you have 2 cross 2 kernel maximum pooling. So, we consider this window first. Maximum of this window is 5. So, we get 5 here. Then we move to next window. We are considering the case of stride 1. Again the maximum is 5. So, we get 5 here. Then we move to this window. Now, the maximum is 6. So, we get 6 here. We move to this window, again we get 6. Next, we move to this window and the maximum is 6. Again, we move to next window, we get 6 here, then we get 5, 5. Then at last we get 6, 6, 4, 5. So, we get this 3/4 convolution output, and it actually preserves the most significant features. The maximum one it preserves. Now, suppose the input at the lth layer is order 3 tensor and the size is PL cross QL cross DL, and the kernel is order 3 tensor with size P cross Q cross DL. Then how we proceed? We overlap the kernel on the top of the input tensor at the spatial location. You may denote it by 0, 0, 0th location. Then we compute the product of corresponding elements in all the DL channels, and we sum the PQDL products, and ultimately it gives you the convolution result at the spatial location. Then we move the kernel from the top to bottom, from left to right to complete the convolution. Now, suppose you have multiple convolution kernels, say T of spatial span P cross Q. So, you are using D convolution kernels, and these convolution kernels are used in that particular kernel layer. Then all the kernels together are order 4 tensor in R P cross Q cross DL cross T. So, in fact, the examples which we have considered earlier uses just one kernel, but you can use multiple convolution kernels also. And suppose you are using D kernels at a particular spatial span, which is of order P cross Q. Then ultimately you obtain the order 4 tensor this. Then index for the specific element of the kernel is I, J, K, L, K, where I varies from 1 to P, J varies from 1 to Q, K L varies from 1 to D L, and K varies from 1 to D. So, ultimately you get this order 4 tensor, and then this is the input size P L cross Q L cross D L, and this is your kernel size, and finally you get the convolution result, which is of the size P L minus P plus 1 cross Q L minus Q plus 1 cross D. Now, suppose you want to make the input and output images of the same size. Then what we do? We insert pad, means say we insert P minus 1 by 2 rows above the first row and P by 2 rows below the last row, and Q minus 1 by 2 columns to the left of the first column and Q by 2 columns at the right of the last column of the input. And then the convolution output will be of the same order, say PL cross QL cross TL. So, if we do this kind of padding, then both input and output images are of the same size, and usually the elements of the padded rows and columns are 0. So, we set the elements of the padded rows and columns as 0. Now, with no stride, we have y or x l plus 1 belonging to R P L plus 1, Q L plus 1, D L plus 1, and then P L plus 1 is equal to P L minus P plus 1, Q L plus 1 is equal to Q L minus Q plus 1, and D L plus 1 is equal to D. And once we apply the convolution procedure, then this is your output of the convolution procedure. And then this equation is repeated for all d lying between 0 to dl plus 1, and for any I l plus 1 j l plus 1 satisfying these conditions. Means I l plus 1 lying between 0 to P l plus 1 and j l plus 1 lying between 0 to Q l plus 1. And in fact, you can express this convolution as a matrix product also. Of course, I am not going into the details, but it can be written as a matrix product. So, in this lecture, we have discussed the architecture and training of convolution neural network. In convolution neural network, we arrange the polling layers and convolution layers in such a way that these layers can extract different features of the data. The convolution neural networks have found applications in various fields like image processing, handwriting recognition, even in analyzing financial time series, etc. So, I am going to stop here. Thank you.
Hello and welcome to this piece of literary snippet. As a student of English literature, the kind of poetry that we are most likely to encounter is perhaps the sonnet. Now, a sonnet, as some of us might already know, is a poem which is composed by putting together 14 lines of verse, and this style of poetry was first popularized by a poet named Petrarch, who lived in Italy during the 14th century. Now, legend has it that Petrarch once saw a very beautiful lady by the name of Laura, and Petrarch was so enamored by the lady that he wanted to compose poems to celebrate his love for her. But there was a problem because marriage was impossible. Petrarch himself was an ordained priest, and that prohibited him from marrying, and the lady herself was a married woman. But nevertheless, Petrarch went ahead to immortalize the beloved and his love for that lady in poetry, and the form that he chose was the sonnet. Since then, sonnets have traditionally been written about ladies who are of unparalleled beauty and about poets who are hapless lovers and who know that their love for their beloved would have to remain unrequited forever. Now, in England, the sonnet form came around 16th century, and its first practitioners were people like Sir Henry Howard, the Earl of Surrey, and Sir Thomas Wyatt. However, it was William Shakespeare who was to prove the greatest of English sonnetteers. And in fact, the charm of those sonnets that Shakespeare wrote 400 years from now still can be felt. And if I read out to you one of Shakespeare's sonnets, you'll appreciate this better. This sonnet is usually known by the title, "Shall I Compare Thee to a Summer's Day?", which is also the first line with which the poem begins. Shall I compare thee to a summer's day? Thou art more lovely and more temperate. Rough winds do shake the darling buds of May, and summer's lease hath all too short a date. Sometime too hot the eye of heaven shines, and often is his gold complexion dimmed, and every fair from fair sometime declines, by chance or nature's changing course untrimmed. But thy eternal summer shall not fade, nor lose possession of that fair thou owest. Nor shall death brag thou wanderest in his shade, when in eternal lines to time thou growest. So long as men can breathe or eyes can see, so long lives this, and this gives life to thee. Now, as you might have noticed, that very much like the Petrarchan sonnet, this poem too speaks of an idealized lover who is more beautiful than a lovely summer's day. But also notice how, in the last few lines, the poem subtly shifts from praising the beloved to praising the poet himself. It is the poet who is going to produce the lines of poetry which will preserve the beloved's glory forever. And people will continue reading them even after the beloved has died. As the last couplet of the poem suggests, so long as men can breathe or eyes can see, so long lives this. And here this, of course, refers to the verse that Shakespeare composes and which we are reading today, 400 years later. So long lives this, and this gives life to thee. Shakespeare is well known for these kind of subtle plays with the conventions, these kind of subtle reversals of what is expected conventionally. But nothing is more striking than the sonnets that he composed on a dark lady. In these poems, we do not meet the traditional fair, idealized beauty, but rather a woman whose appearance might even be described as ugly. Here is a sample. My mistress's eyes are nothing like the sun. Coral is far more red than her lips is red. If snow be white, why then her breasts are dun. If hairs be wires, black wires grow on her head. I have seen roses damasked red and white, but no such roses see I in her cheeks. And in some perfumes is there more delight than in the breath that from my mistress reeks. I love to hear her speak, yet well I know that music hath a far more pleasing sound. I grant I never saw a goddess go. My mistress, when she walks, treads on the ground. And yet, by heaven, I think my love as rare as any she belied with false compare. As you can see, the beloved described in this poem is nowhere as beautiful as a beloved of the first poem. Yet, the point that Shakespeare is making here is that though the image of the beloved is not as beautiful as it was in the previous poem, it doesn't stop her from being an object of love. Love, Shakespeare insists, has very little to do with the outward appearance of a person. And in many ways, this de-idealized beloved is perhaps a person with whom a more intimate engagement is possible. She is definitely a more human person, a person who treads on the ground just like all of us do. See you in the next episode of Literary Snippet.
Understanding oneself, understanding others, understanding society at large, understanding the nature, these are all driven by basic human curiosity. We would all love to understand why things happen, what happens, what is the final outcome, why certain things fail. These are all exercises that we perform in various domains of knowledge. Therefore, knowledge in various domains, you would realize they are actually social artifacts. They have to be rooted into historical perspective, they have to be culturally salient, and there would be socio-political reasons behind this. Whether you talk with respect to engineering sciences, whether you talk with respect to physical sciences, biological sciences, social sciences, that is the reason why humanities and social sciences should be understood by all of us. The knowledge that is segregated, that is divided with respect to areas, specializations, all of them needs to be understood in its context. And what provides the context? It is the social reality. How do you correlate knowledge in a given domain with the cultural reality, with the social reality, with the socio-political compulsions? Okay, how do you understand the law of nature, okay, in its totality? And for doing that, you require the understanding of humanities and social sciences. Say for instance, if you are trying to understand the effect of a particular bacteria, a virus, any microbe, how it affects behavior, how it affects the organism, human being, you start looking at it from a pure biological point of view. If you are trying to look at a particular type of a wavelength, say for example, you are emphasizing on the understanding of the effect of radiation on human life, you are looking at things from a physical point of view. You are looking at the corresponding changes inside the body, you are looking at the physiological side of the understanding of the information. You are trying to understand why, despite knowing the risk that is inbuilt in the process, why still human beings engage into it. You are looking at it from a pure behavioral point of view. Why society at large admire things which has full of risk. You are trying to understand things from a pure sociological point of view. Why people use particular set of words to explain those experiences. You are trying to understand things from the linguistic point of view. So, there are whole lot of things, and then finally you try to combine all of them to say that what are the guiding principles in life. Then you say you are looking at life, you are looking at humanity from a pure philosophical point of view, and this is what social sciences courses provide you. They provide the context to you in which you would be finally positioning the understanding of the knowledge in any given domain. It could be engineering, it could be sciences, it could be medical sciences, it could be social sciences stuff, it could be humanities stuff. So, contextualizing the knowledge is what humanities social science courses help you obtain.